A weathered engine sits behind velvet ropes in a museum, its massive bell frozen in silence. The metal is cold now, dormant, but archival footage tells a different story. 5 of these engines igniting as one, creating a wall of flame 300 feet wide, consuming the launch pad as the Saturn V claws its way toward the sky. The placard beside the museum piece reads, "The most powerful rocket engine ever built." In the 2010s, NASA engineers tried to do something that should have been simple: understand one of their own engines. They had the original blueprints, they had the specifications, they had computing power that would have seemed like magic to the Apollo-era engineers. They used laser scanners to capture every dimension with impossible precision, creating perfect digital twins of engines that had been built half a century ago. Then they ran their simulations, feeding all that data into computational fluid dynamics software that could model the behavior of gases and flames with breathtaking accuracy. And the computer told them something impossible: the F-1 engine shouldn't work. Yet this engine, the most powerful rocket engine ever built, flew 65 times without a single in-flight failure. It carried 24 humans to the moon. The computer said it was impossible, but it worked. It worked because the F-1 didn't succeed because of the blueprints. It worked because of the people who built it, the welders who knew exactly how to angle their torches, the machinists who could feel when a cut was right, the engineers who learned to hear trouble in the song of a turbopump, the technicians who knew each engine's personality. And those people and their knowledge are gone. This is the story of the most powerful machine ever built and the irreplaceable human expertise that made it possible. This is the story of how America reached the moon and then forgot how it got there. The F-1 engine was a monster. Each engine produced 1.5 million pounds of thrust. To understand what that means, you need to grasp the sheer violence of controlled explosion contained within its metal walls. 5 of these engines, mounted to the base of the Saturn V rocket, generated 7.5 million pounds of thrust. That's the power needed to lift something impossibly heavy off the ground and hurl it toward another world. The Saturn V, fully fueled and ready for launch, weighed 6.5 million pounds. Think about that for a moment. 6.5 million pounds. That's the weight of a Navy destroyer. That's more than the combined weight of every car in a large parking lot. And the F-1 engines had to lift all of that mass. Not slowly, not gradually, but with enough acceleration to overcome Earth's gravitational grip and punch through the atmosphere. No existing engine came close to the required power. This wasn't a matter of making incremental improvements to proven technology. This was a quantum leap into the unknown. The engineers at Rocketdyne, the company tasked with building these engines, faced an impossible mandate from President Kennedy: build an engine powerful enough to send humans to another world, with technology that doesn't yet exist. Do it before the Soviets. Do it before the end of the decade. Do it or lose the space race and abandon humanity's greatest adventure. The scale of what they attempted defies comfortable comprehension. Each F-1 consumed 3 tons of propellant every second. Think about that. 3 tons every second. That's 15,000 gallons per minute of liquid oxygen and kerosene being forced into a combustion chamber and ignited. The result was a continuous controlled explosion that had to be sustained for minutes at a time without destroying the engine itself. And yet, despite all this power, despite all this violence, the engineers who built the F-1 faced a problem that threatened to end the moon program before it began. The engine kept exploding, not during flight, during testing. The F-1 was tearing itself apart before it ever left the ground. The explosions had a name: combustion instability, and it would become the F-1's greatest enemy, a physics problem so complex that even today we don't fully understand it. Imagine you're in a cathedral and you clap your hands. The sound bounces off the walls, creating echoes. Now, imagine instead of a simple clap, you're creating a continuous roar of sound, and instead of stone walls, you're inside a metal chamber where gases are burning at temperatures that would vaporize most materials. The sound waves, pressure waves really, bounce off the chamber walls. In a small space, these waves dissipate harmlessly. But in a combustion chamber the size of the F-1's, something terrifying happens. The waves begin to reinforce each other. They amplify. They grow stronger with each reflection until they're no longer just sound. They're physical forces capable of tearing metal apart. This is combustion instability. When the burning fuel creates pressure waves that bounce off the chamber walls, amplifying into violent oscillations that can destroy an engine in milliseconds. At the F-1 scale, these oscillations created forces equivalent to hundreds of tons, battering the engine structure thousands of times per second. It was like trying to contain a continuous bomb explosion inside a metal box. The test engineers at Rocketdyne watched their engines destroy themselves. The combustion chamber would begin to shake. Then the shaking would intensify, becoming violent, chaotic. Cracks would appear in the metal, fuel would leak, and then the entire test stand would be consumed in an uncontrolled explosion. Each failure set the program back. Each failure brought them closer to missing Kennedy's deadline. Each failure meant the Soviets were winning. Traditional solutions didn't work at this scale. Small engines could use simple baffles or injector designs to prevent instability, but the F-1's enormous combustion chamber created acoustic patterns no one had encountered before. The physics were well understood in theory, but theory and practice diverged wildly when you tried to scale up to this level of power. The engineers faced a paradox. They needed to test the engine to understand the instability, but the instability destroyed the engine during testing. The Rocketdyne engineers realized that conventional aerospace engineering, the world of precise calculations, specifications, and theoretical models, wasn't going to save them. They needed to try something else, something more like art than science, something that would later be called, with a mixture of pride and bewilderment, black magic. What happened next was unprecedented in aerospace engineering. They stopped trying to calculate their way out and started experimenting their way through. They would try something, test it, watch it explode, learn from the wreckage, and try something else, over and over and over again. The solution involved adding baffles to the injector plate, metal barriers that disrupted the pressure waves before they could amplify into destructive oscillations. But determining the right design required testing hundreds of configurations. Each configuration required building a new injector plate, installing it in an engine, mounting the engine on a test stand, fueling it, igniting it, and hoping it wouldn't explode. Often it did. The engineers conducted over 3,000 full-scale tests of the F-1. 3,000? Many ended in explosions. Each test was expensive. Each test was dangerous. Each test risked the lives of the technicians who worked the test stands. But they kept testing because they had no choice. The moon wouldn't wait for elegant theoretical solutions. They developed testing methods that seemed insane. They would deliberately bomb engines with small explosives during operation to see if they could survive induced instability. They were essentially stress testing by trying to make the engines fail in controlled ways, hoping to understand the boundaries between stability and catastrophic destruction. It was brutal, empirical engineering at its finest and most desperate. The final injector design had 13 baffles in a specific pattern. And here's the thing that haunts modern engineers. The Rocketdyne team couldn't fully explain why this pattern worked. They only knew that it did. Computer models suggested other patterns should be equally effective, but testing proved otherwise. The knowledge became embedded not in equations, but in results. This works, that doesn't. We don't know exactly why, but we know it's true because we've tested it 3,000 times. Critical knowledge became embedded in the technician's judgment in ways that no manual could capture. A particular sound meant trouble. A specific vibration pattern indicated an impending failure. Some variations from specification were acceptable. Others were fatal. But which was which? That depended on context, on experience, on an intuitive feel for the engine's behavior that took years to develop and couldn't be reduced to a checklist. The F-1 worked. But it worked in a way that defied complete documentation. The solutions were empirical, not theoretical. The knowledge was in the hands and ears of the people who built it, not in the manuals. But the people who understood these nuances, who could feel when an engine was right, they didn't work alone. The F-1's success depended on an entire ecosystem of specialized craftspeople whose skills would prove even more irreplaceable than the engineer's theoretical knowledge. Each F-1 required over 5,000 welds. 5,000. Many of these welds joined exotic materials under extreme precision requirements. The welders who performed this work weren't just following procedures, they were artists. They developed techniques that weren't in any textbook. Subtle adjustments in torch angle, in timing, in heat application that made the difference between a weld that would hold under the stresses of launch and one that would fail catastrophically. A weld that looks perfect to the naked eye might have internal stresses that will cause it to crack under vibration. A weld that meets every measurable specification might still be wrong in ways that only an experienced welder can sense. The master welders who worked on the F-1 could feel these differences. They knew when a weld was right, even when the instrument said it was merely within tolerance. Machinists worked to tolerances of thousandths of an inch on components several feet across. Imagine trying to machine a piece of metal the size of a dinner table to a precision measured in the width of a human hair. Now imagine doing it with materials that behave differently under different temperatures, that flex and warp as you work them, that have grain structures and internal stresses that affect how they respond to cutting tools. The machinists developed an intuitive sense for how materials behaved under their tools, that no computer numerical control program could replicate. Because CNC programs follow instructions without understanding, the machinists understood. The turbopump was perhaps the most demanding component of the entire engine. It had to feed 3 tons of propellant per second into the combustion chamber. 3 tons every second. The pump spun at thousands of revolutions per minute, moving liquids at pressures that could cut through steel. The precision required for this component was almost absurd. The slightest imbalance would cause vibrations. Vibrations would cause wear. Wear would cause failure. And failure of the turbopump during flight meant the destruction of the rocket and the death of the astronauts. Technicians learned to identify problems by sound alone. The turbopump produced a complex acoustic signature during operation, a song of spinning metal and flowing liquids. Experienced technicians could distinguish between dozens of different acoustic signatures, each one telling them something about the pump's condition. This bearing is wearing. That seal is starting to leak. This vibration pattern means the balance is slightly off. They could hear things that instruments couldn't measure because they had learned to listen with years of experience. Workers learned each engine's personality. Yes, personality. Because even though every F-1 was built to the same specifications, each one was subtly different. Individual quirks and characteristics that fell within specification but affected performance. One engine might run slightly hotter. Another might have a particular vibration signature. These differences weren't defects. They were the natural variation that comes from building something at the absolute edge of what's physically possible. And the workers learned to recognize these personalities and make undocumented micro-adjustments during assembly based on this intimate knowledge. This expertise took years to develop. A master F-1 welder or machinist represented a decade or more of accumulated experience, much of it learned through mentorship and hands-on practice rather than formal training. You couldn't become an F-1 craftsperson by reading a book. You had to work under someone who knew, who could show you, who could tell you when your weld looked right and when it didn't, who could teach you to hear what the turbopump was saying. This tribal knowledge, passed from master to apprentice, learned through feel and experience, was never fully documented because no one realized it needed to be. The F-1 worked so reliably that the knowledge seemed permanent, as solid and enduring as the engines themselves. Between 1967 and 1973, the F-1 flew 65 times, 13 Saturn V launches, 5 engines per launch. Not a single in-flight failure. It was a perfect record. The most powerful rocket engine ever built, and it never failed when it mattered. It was a triumph of engineering, of craftsmanship, of human ingenuity and determination. It was proof that we could do the impossible. And then, almost overnight, it all ended. Apollo 17 launched in December 1972, the last time an F-1 would fly. The Saturn V rose one final time, its engines burning perfectly, carrying the last humans who would walk on the moon in the 20th century. It was a perfect launch, a perfect mission, a perfect ending to the Apollo program. Except, it wasn't an ending. It was an abandonment. By 1973, the production lines were shut down. The tooling, the specialized equipment used to manufacture F-1 components, was scrapped or mothballed. The The workforce was dispersed. Thousands of specialized workers, welders, machinists, engineers, technicians, were laid off or transferred to other programs. Many left the aerospace industry entirely, some retired. The master-apprentice chain was broken, the community of expertise dissolved. The institutional knowledge base fragmented. Engineers moved to different companies, taking their experience with them. Technicians who knew the engine's quirks found work elsewhere. Welders who had spent years perfecting their craft applied those skills to different projects. The network of people who collectively understood how to build an F-1 engine scattered across the country, across industries, across the remainder of their careers. Documentation existed, of course. Thousands of pages of specifications, blueprints showing every component in precise detail, test reports documenting the results of those 3,000 tests, manuals explaining assembly procedures. All of it was carefully archived. NASA and Rocketdyne believed they had captured the essential knowledge required to build an F-1. But these documents captured the what, and not the how or the why. The blueprints showed the dimensions, but not the subtle adjustments. The specifications listed the tolerances, but not the intuitive judgment about which variations mattered. The test reports documented the results, but not the accumulated wisdom about what those results meant. The subtle adjustments, the workarounds, the intuitive knowledge, none of that made it into the official record because no one realized it was knowledge worth recording. It seemed like common sense, like craft, like the kind of thing everyone just knew. NASA and Rocketdyne didn't see this as a crisis because they didn't anticipate ever needing to build F-1s again. The space shuttle was the future. The F-1 was history, a magnificent achievement that had served its purpose. The engines would go to museums. The knowledge would fade into memory. And that was fine, because we were moving forward, not backward. For decades, this didn't matter. The F-1 was a museum piece, a relic of a bygone era when we had the will and the budget to do impossible things. Children pressed their faces against the glass to stare at these giants. Engineers regarded them with respect and nostalgia, but they were history. But then, in the 2010s, NASA started thinking seriously about returning to the moon, about going to Mars, about launching heavy payloads beyond Earth orbit, and they realized they might need engines with F-1 class power. The new space launch system would need enormous thrust to escape Earth's gravity with the mass required for deep space missions. That's when they discovered what they'd lost. In 2013, NASA engineers began a project to study the F-1, hoping to learn lessons that could inform future engine designs. They approached the task with the confidence of modern engineering. They had tools the Apollo-era engineers could only dream of. Three-dimensional laser scanning that could capture every surface, every dimension with precision measured in microns. Computational fluid dynamics software that could model the behavior of gases and flames inside the combustion chamber. Computer-aided design systems that could visualize and analyze components in ways impossible in the 1960s. They scanned museum F-1 engines, creating perfect digital models. Every curve, every weld, every surface captured in exquisite detail. They fed this data into their simulations, expecting to confirm what they already knew, that the F-1 was a brilliant piece of engineering that worked exactly as designed. Instead, they discovered something deeply unsettling. The computer said the engine shouldn't work. The simulations predicted combustion instability patterns that should have torn the engine apart. The injector design that had worked perfectly in reality, that had flown 65 times without failure, performed poorly in the models. The baffles were in wrong positions according to modern computational analysis. The combustion chamber should have experienced destructive oscillations. The engine should have been unstable. But they flew it 65 times. It worked. It took us to the moon. The modern engineers realized the original builders had solved problems through empirical testing that modern theory still couldn't fully explain. The F-1 worked for reasons that weren't completely understood even by the people who built it. It worked because 3,000 tests had found a design that functioned, even if the theory couldn't explain why. It worked because skilled craftspeople had made thousands of small adjustments that weren't in the blueprints. It worked because human expertise had bridged the gap between theory and reality. The engineers tried to understand how to manufacture new components using modern techniques. Surely modern manufacturing, with its computer-controlled precision and advanced materials, would make building F-1 components easier and better. But they discovered another layer of lost knowledge: modern manufacturing techniques, which were better in every measurable way, produced parts that didn't behave the same way as the originals. The original components had been made with 1960s-era equipment and techniques. They had subtle characteristics, surface finishes, internal stresses, material properties that resulted from those specific manufacturing methods. Modern equipment produced components that met or exceeded the specifications, but they were different in ways that mattered, ways that the original craftspeople would have understood intuitively, but that weren't captured in any document. The F-1 worked because of the people who built it, not the blueprints, not the specifications, the people. And those people and their knowledge were gone. The realization was humbling and frightening. We had built the most powerful rocket engine in history. We had used it to accomplish humanity's greatest technological achievement. And then we had forgotten how we did it, not because we were careless, but because we didn't understand what knowledge was. We thought knowledge was the blueprints, the specifications, the test reports. We didn't realize that knowledge was also in the hands of the welders, the judgment of the machinists, the ears of the technicians, the accumulated wisdom of people who had spent years learning to feel when something was right. We can look at the F-1 engines in museums. We can measure them. We can scan them. We can create perfect digital models. But we cannot recreate them, not exactly, because the knowledge required to build them walked out the door when the Apollo program ended. That knowledge retired. That knowledge died. That knowledge was never passed to a new generation because we didn't realize it needed to be preserved. This is the tragedy of the F-1, not that it stopped flying, technologies become obsolete, but that we lost the ability to understand our own greatest achievement. We reached for the moon and we made it, but in doing so, we learned something we didn't expect: that human expertise, human craft, human intuition are not easily captured or transferred. That knowledge is not just information, but understanding, that we can write down what we did without preserving the wisdom of how we did it. The F-1 engine sits in museums now, silent and cold. Children still press their faces against the glass. Engineers still regard these machines with awe, but now that awe is tinged with loss, because we know we built something magnificent, and we know we cannot build it again. The blueprints remain, the specifications endure. But the people who knew, who really knew, are gone. And with them went something irreplaceable, the knowledge that sent us to the moon. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.